My name is Chris Zappa. I'm a professor at Lamont Doherty Earth Observatory at Columbia University in New York. Columbia University is in New York City. Lamont Doherty is up the Hudson River about 10 miles from the city. So it's a nice bucolic area. My background is, as an undergraduate, I was an engineer, mechanical engineer. And then I went to University of Washington and I studied oceanography. So I have both a technical and a kind of physics science background together, and it kind of really goes well with what I study, which is atmosphere-ocean interaction. And today I'm going to talk about blend of both of those aspects, both the technical aspects of how I observe the physical processes, and I'm going to talk about the processes themselves, just so you have some background as to why I'm observing these processes. So from the technical standpoint, for the last, say, 10 years, I've developed UAV imaging or UAV payloads. So I don't build the UAVs themselves, the platforms, and I don't do the control systems for platforms like many of you do here do. I build the observing components. And a lot of those components or systems evolved from what I used from ships and used from towers and from other platforms that are not tiny and autonomous. And these are just some. Most of the UAV work that I've done has been funded by NASA and two foundations: the Moore Foundation and the Schmidt Foundation. And the four guys at the bottom here are my technical engineering team, field team, engineering team, everything. So I'm going to start right in with some science first. So when I first started graduate school, I study how ocean atmosphere carbon flux varies around the globe. This is a map of CO2 flux, and you can see in the equator there's lots of CO2 going into the atmosphere, so those red areas, and then in the higher latitudes, mid-latitudes, there's a lot of CO2 going into the ocean. And when you sum all these up, that tells that the net carbon uptake by the ocean is about 2 gigatons. So what I study, so there's someone at Lamont who studies this, how much CO2 is in the ocean and how much CO2 is in the atmosphere. But I study the physical part here, the rate of transfer across. So you can have no difference between the ocean and the atmosphere. Hold it up higher? Really? Like this? Okay. You can have no PCO2 difference, and you won't have any flux, even no matter how energetic the ocean is. But you can have if you have a lot of CO2 difference and just a little small waves, and they can make a big difference in how much CO2 uptake you have. So one of the people go out, they measure gas transfer, they look at how fast it goes into the ocean and out, and they have all these measurements, and you can see there's all this scatter everywhere. So we want to try and this is the rate of transfer as a function of wind speed. And there's two kind of arguments. One is there's a cubic dependence, which because of wave breaking you have bubbles, or a quadratic, which is a u squared dependence, and that's basically due to, say, momentum flux. So I am trying to minimize all this scatter here. You see out here these wind speeds in the measurements, and come up with a better model. And to do that, I'm studying various processes. So we look at the wind, how the wind generates waves. The waves eventually will break, and they'll generate bubbles. You'll have small waves that break that don't generate bubbles. You'll have secondary flows like laminar circulation, which export lots of CO2 from the ocean downward. You'll also have precipitation, which also mixes up the surface. So all these processes, and you'll have the heat budget, which generates buoyancy. So all these processes affect the turbulence in the ocean, and the turbulence is what is driving the transfer. So we can have a simple model for that transfer rate that scales with this epsilon here is the turbulent kinetic energy dissipation rate. So it's how much energy is being dissipated out of the system that goes to heat. So we can scale it based on that, and we can measure this in a number of ways. But this scaling actually works really well to collapse all that data, whether it's in an estuary, and this isn't working right now. Come on. Oh well, those were infrared movies to show some features, but I think the next one will show it nice. There we go. So this is an infrared image of rain. First it's just the ocean surface, right? And it's cool, and then there'll be these black dots. You'll see, there they are, see the black dots, those are the rain. They hit the water, and they start mixing it up. And that mixing is what's enhancing the transfer across the ocean interface. And you can think of breaking waves doing the same thing, mixing up this surface layer. So that model I showed you collapses the data that we took, which is all scattered here on the bottom, K against the wind speed parameterization. Here, that transfer rate scales with that turbulent dissipation rate that I just showed you. So we're getting somewhere, but what you'll notice is out here, this is really high wind speed, so this is where there's big breaking. And here's that the cubic that I was talking about, here's the quadratic, and you can see there's a significant difference between the two. So one of the ways that you'll see that can disrupt the surface are these small scale waves that don't entrain air, but they still mix. And we have this camera that measures these small scale waves. So that's the slope. This is a slope camera. So it measures it's kind of jittery on here. But you can see all these capillary waves of the ocean surface. You'll see some breaking waves coming through there. There's a breaking wave. And that's what's disrupting the surface, and that will enhance the transfer rate. And there we go. This is just the integrated slope field to get the surface topography. And then this is what you can get the nice wave number spectrum of the surface waves. So getting the scales of waves has never been done before. So we've been doing this developed this in the last 5 years. And you can learn a lot about the transfer processes from studying these small waves. But we're interested in the big waves. And the big waves, let's see, there it is. So this is what it's like at sea. I don't know if anyone has gone to sea, but this is what I live for this. And so it's not too bad right now, but we want, see how chaotic it is. It's tough to put things in the water. You'll see some breaking waves in there. And eventually, the observer is going to take a fall, because you'll see the camera go sideways. So there's a nice breaking wave out there. But we want to be able to characterize this using various techniques. And one, I think Christopher yesterday spoke about looking at ice and measuring the sea ice distribution with a camera. We do the same thing with, here we go, boom. So a wave just came over and hit the observer, and they took a fall. Anyway, that's what it's like at sea, and it's a lot of fun, if anyone wants to go. So we put things out like a wave rider buoy to measure the wave field, and this is where we just were just now in that video. You saw that big storm right there that came over and hit Europe. That was about 2 years ago. But things like this can survive those kind of storms and give us really valuable data. But similar to what, like I said, Christopher talked about yesterday, where he was looking at sea ice, here we're looking at those white caps and trying to capture, they're not stationary like the nice sea ice is. It's actually moving. We have to do all the same kind of distortion corrections that Christopher was doing. And we get the actual crest distributions and then how fast they're moving. And from how fast they're moving, we can model breaking better and come up with a better estimate of the transfer rate. So skip that. So remember again, there's the three types, cubic and quadratic. This is a linear, this is like the original scaling model. But you can see the data that from all the experiments that we were on, you can see we saw both the cubic and the quadratic, and actually the linear as well. And when we use these wave statistics models that we are able to measure with the visible, with the polarimetric camera, with the buoys, we can collapse that data really nicely using either a model that includes both wind speed and wave height, and also similarly that includes wave age. So how old are the waves? So young waves are much more energetic and will dissipate more energy. So we've made a lot of progress by observing or coming up with better ways to observe waves and then use that to model the process we're trying to understand, the gas transfer. So if you come up with anything, we're able to collapse the K conundrum. We could talk to your colleagues, impress them. But that's our latest discovery. So all the measurements I've shown you up to now have been from ships. So we were out on this ship. We put our measurements out on the boom like this to get away from the ship. We put them up on the towers here, up here, on these towers as high up as we can, and away from the superstructure as much as possible. We also, yeah, sure. Yeah, interrupt as much as you want. So you mean in that sea that I was just showing you, what's it like? It'll submerge. So the bow will go underwater. We won't put this out when it's like that. That'll stay in. But yes, when we're steaming along in those kind of conditions, it'll go into the underwater, but it pops right up.
No, but I was wondering, if the wave hits
Yes?
the ship, then you get reflection.
You do.
This mix.
Most waves that hit the ship, basically first thing we point into the wind. So it cuts the waves, it's cutting through the waves, and you get a Kelvin wave that goes back. But I know what you're saying. If we were broadside to the waves, you get reflections off for sure. But we always face into the wind to make sure we get good fluxes and the waves don't contaminate.
But I guess I'll say also complement Pedro's question, I think that is how can measurements get directly by, say,
So whenever we put an instrument out, we're always measuring the ship motion. So if I have a camera out, I have a 6-axis IMU with it. Any instrument I put out there always has an IMU with it, so I know I can characterize it locally. And the ship itself has a high-end IMU, so it knows how well it's doing. There are other issues. When you're measuring the flux, the superstructure itself contaminates. So that's part of what I'm getting at, is that the whole point of using UAVs is to get away from the ship eventually. So I was just getting to that point. No. So as you can see, we do try and get away from the ship a little bit by measuring our fluxes out here. But as Joao and Pedro mentioned, Pedro, right? Pedro. You'll have distortion by the superstructure. And it's been modeled, certain ships have been modeled in terms of what their flow distortion is, so you can do some corrections, but it's not ideal. We also get even farther away from the ship. We'll put out drifting buoys like this. We'll measure the fluxes here. We can put other simple instruments on there and do similar studies here, but again, you can't put this in, you can put it in those kind of conditions, but it's going to be really difficult to make the measurements or come back with good measurements. You can put little catamarans out like this, or we put our imaging systems on it and measure the waves here. So this is a slope gauge. This is an infrared camera. It has the flux packages on there. There's a similar catamaran, very, very well instrumented. This one specifically was measuring the flux and turbulence in the water. So we have all these autonomous platforms to go away from the ship. But I want to be able to map larger areas with using the UAVs. So we set out on developing these, taking all those measurements that I was making from the ship, and putting them on UAVs to two things. It allows us to get away from the ship, and it also allows us to go get greater coverage away from the ship and characterize processes at much more advantageous conditions. So as I mentioned, the first project was funded by NASA up in Alaska. This is called MISOPEX, the Marginal Ice Zone Observations and Processes Experiment. Then, after that, the Moore Foundation funded me to develop some more payloads. Then the Schmidt Foundation funded me to put those payloads on VTOL systems. And the Moore Foundation just funded me again to go back to Alaska to work with indigenous communities, looking at sea ice and how it affects their community. And then the Schmidt Foundation funded me again to go back out in 2 more years to do well, I'll talk about what we're going to do. So this is the first experiment, was up in Aliktok. Here we used a Scan Eagle. I'm sure all of you have seen the Scan Eagle before. It has the catapult system like you've seen. It has a cool recovery system. It can go for, I think these go, it says 20 hours. We went up to 10 hours at a time. The payload capacity was 6 pounds. We stuck with that. And this, oh, come on. What? So here's the deployment. Everyone's seen that. That's not as exciting. But this is the crazy one. I'm not a big fan of this, but this is why I went away from this idea. It's going to come from the left. There's this boom with a rope on it. Woo! So when I put my $100,000 instruments on there, I don't like that. So I'd rather move on to something a little easier. But when we're up there, this is in the marginalized zone off of Alaska. You see these big icebergs, and this is the visible imagery on the left. This is an infrared image on the right that corresponds to this box. So you can clearly see the ice here, and I'm using a cooled camera here. So I was flying a cooled camera. So you can really see the sharp temperature gradients that, well, they're fine temperature gradients, so they're very sharp, and the point is that, well, 2 things. You can see the iceberg here is cold, right? Black is cold, white is warm. You can see this river, this melt river here, going into the ocean, and you can see this cold water on the surface, so it's cold, fresh water from the ice melt. But you can see it has like a wake to it, so all these little wakes coming off, all these little pieces of ice, if you up here closely, they all have like little wakes on them. So 2 things, you can use the wake to determine the direction of the current. You can actually, when you're flying over, we use PIV to get, when there's no ice, to get motion of the ocean surface. You can use the ice itself to get motion of the ice. And eventually, all these we can characterize how the ice itself is mixing, or adding mixing to the ocean. So you can think of all these like a big one here. If there's current going by it's generating turbulence as a boundary layer underneath it. So it's adding turbulence to the system. And these are flights. This is temperature. And what I wanted to say here was that it's not necessarily the gradient in temperature isn't really what we're after here, but it's the variability in temperature. So here the variability is very small and it increases significantly. So here the variability is up to 1/2 degree, and we're talking about small scale variability, not this large scale gradient. And the idea is that because you have more ice here, it's generating more mixing, so it's smoothing out those temperature gradients, so it doesn't have as much variability. The ice melts away, it adds cool water, which is very different than the temperature of the water behind. And it's also, as it's melting, there's less ice to mix. cause mixing. So you have much larger variability in the temperature gradient, in the temperature variability. And this is important in terms of looking at the heat budget for the ocean atmosphere. So that's something that you can only do that with UAVs, especially in the Arctic, because typically satellite coverage is sparse. It doesn't have many repeats to begin with, and then when it does repeat, it's usually cloudy, so you don't have there's hardly any satellite data. So this is the one day we were out there for the whole month, where we had a nice clear satellite image. And you can see that the gradient that we see in this box here is this area here. And we can see that the same temperature gradient, but we also see a lot more structure. So we get coverage whenever we want, and we get much finer detail in terms of what's going on. So that was a simple payload, just infrared visible imagery. And then, as I mentioned, the Moore Foundation funded us to develop a whole suite of new payloads. And that experiment was geared towards going up to Svalbard in Ny-Ålesund to test there, because that's where we met Rune. We had a relationship with No Root. And we used the Manta this time. So it had a catapult system not just like, but it's similar. It was a catapult launch, but it had a landing gear, so we would much smoother landing. But for this project was developing a concept of hot swappable payloads. So the idea was we had a base payload which had the power, the computing, the acquisition, the storage, both like a DAC, an A to D system, and also an image acquisition system. And then we could swap in whatever payload we want, instruments we wanted, depending on what the objective was. So here's the base payload, and then we would add in, say, our long wave and short wave radiometers, up and downward looking, to measure the radiation budget for the Earth system. And then here's that payload here. You can see the domes right there. That's it more close up. We also had, and with that, we also had a little camera here. And then, so this is the temperature data from that. This is, so every payload has an upward downward looking radiometer to measure sky temperature and whatever you're looking at on the ground. So whether it's ocean temperature, ice temperature, land. And that's what this is. This is the temperature from that radiometer. And you can see, so here's the water, right? Here's the land with ice on it. We're like right up here, this is the runway right here. So over land, it's very cold, or colder, you know. Over land, it's colder, over the snow. Then over the water, it's warmer. And then over here, even though it's over the water, at this time, there was lots of sea ice. So we're measuring the sea ice variability in the IR there. Then we go on land. So this must have pushed back since that image, because that's the glacier coming down. So it must have calved a few times. And then that's the glacier edge. This altitude, we normally fly at around 3,000 feet, 1,000 meters. So one thing you'll notice here, the ocean is a lot warmer than the land. So the one nice thing about going and doing work in the polar regions when you're on a ship is that it never gets cold, because the ocean is always going to be at least 0, and it keeps you warm. So whenever on a ship, most people are just wearing shorts because it's so hot on the ship itself, even though you're like in the air temperatures, whatever, minus 20. So another payload we developed is this, what I call dropson microbuoy, so the DDMD. And basically it's this spring system where we put our little dropsons in there, and it deploys. And actually, better discussion is here. So we're flying along, we drop them, and it measures the temperature and humidity in the atmosphere. And that's what's over here. Here's the temperature in red, the humidity in blue. You can see that inversion there at, the boundary layer where you would expect it to. And all that data is being telemetered back to the aircraft. It's also being stored on the buoy. When it hits the water, it becomes a microbuoy, which deploys a temperature and salinity measurement at 3 depths, or however many depths we want. In this case, it was 3. And that data is stored on board, but also telemetered back whenever the aircraft's there. So we can, and this will last about 2 weeks. So we put them out there, the measures temperature, salinity the whole time, stores it on board. When we go back out and fly overhead, all the data gets telemetered back to the aircraft. If we're within line of sight, like in Svalbard, we could telemeter the data directly back to our home base if we have a nice image. So this is actually a really nice system where you can go into leads or ice and just drop the little microbuoys in there and get measurements that you wouldn't normally get because you can't get a ship in there. So there's.
Are the drop points kind of pre-planned, or those are kind of selected on the line?
Say that again?
Drop points.
The drop points.
Yeah, when you decide to.
They're planned, but we can also we trigger it. Yeah, totally. We don't. They're about $500 a piece, so we don't. We just go away. We could but the point is we're putting in places where we can't get with a boat. But if you're just putting them to get away from the ship, we can always go out and get them with a rib or something. So these are just 2 more payloads. We have hyperspectral image. Whoops, wrong one. Hyperspectral imaging, both visible near infrared and the near infrared. And this is, so right now, this is our suite of payloads. A visible thermal, just like we had on the Scan Eagle. So we just transferred it over. A cooled camera, a cooled infrared camera, hyperspectral visible, hyperspectral near infrared. I didn't show this, but it has we have a LiDAR system and also a turbulent MET package. So similar to what, the same idea that, not the same idea, but what Andreas was talking about yesterday, looking at the turbulent wind. We have a similar sensor on there that measures the turbulent wind. The radiation one I mentioned, and then it drops on. We're also working on another one, Falcor. But working on another one now to measure sea ice thickness. We're always working on developing new payloads. So, yeah. Yeah.
How do these affect the, let's say, flight plans or kind of the flight patterns depending on the type of sensors?
Yeah, all right, so good question. So typically all the imaging payloads, we like to fly at around 1,000 meters. So we get good, a roughly 500 meter square swath. So there's 2. One's the hyperspectral cameras are actual push brooms, so it's a line with all the bands, all the spectral bands, makes up the imager. And the infrared camera is a true camera, so it's measuring snapshots at 100 hertz as we fly over, so we can do both. Yeah. The LiDAR MET package, we like to fly lower, so because you want to measure the flux as close to the surface as possible within safety standards. The radiation, we would fly at all altitudes, from the surface all the way up to, say, 10,000 feet or meters, as far as the plane will go. Because the radiation, you can look at how the atmosphere affects the radiative balance coming in. And then these you'd like to drop these at around 500 meters or less, just so it lessens the impact. I guess it doesn't matter. It's going to reach terminal velocity, and then who cares? The terminal velocity with the little flag we have on there, our drogue. But from a science point of view, what our flight plans are and how many of these we use simultaneously depends on what we're looking at. Typically, I like to fly the MET package with either the radiation, so that would be the total heat budget here, or the LiDAR or the MET package with the visible or the thermal camera. And I'm going to get to it, but our next Falcor cruise will be heavy with the, actually, we're going to develop a new hyperspectral camera that's even more sensitive, because
So how many drones, drifters can you carry? How many?
how many drifters can we carry per payload? Yes, so we have multiple sizes, so we can carry 4 maximum. That was on the Manta, which had only a 6 pound payload as well. The new payload, or the new systems we're going to. So, one second. The Falcor funded us to take all those payloads and put them on this VTOL system. And the VTOL system has a payload of roughly, say, has an endurance of around 20 hours, a true endurance of 20 hours, a true payload weight of at least 10 pounds, and you can give up fuel for payload. So if I don't want to fly, if I don't need to fly 20 hours, say I want to fly during the day, I can go 8 hours and get 5 pounds of payload, 5 pounds of fuel towards the payload. So we use this system to put all our payloads on this system. So it's a vertical takeoff and landing. And I have a couple of images. So it's really a pretty cool system. But I want to show a couple videos. Oh, this is landing. Hold on. Not that one first. Let's do... Oh, what? Hold on. Oh. Is it over? Oh, this happened before. How does this work?
We could see it before when you.
I know, but then I can't start it.
Oh.
Oh, yeah, good point. There you go. Woo. And up, huh? Uh-oh. That'll work. No, not really. I don't know. Watch what, let's see what happens. This could be dangerous.
Looks good.
Yeah, but, okay, all right. So, I'm gonna skip a little bit here. So the ship is 45 degrees to the wind. So that's the stern, that's the bow. The wind's coming off the bow like this. So it's directed into the wind. It just transitioned and now it's going to fly off. It's gone. So it transitions from the vertical takeoff, which is all battery driven. You have like 3 minutes of battery time. So you better get up off the ship and within 3 minutes. And you also, actually that's both takeoff and landing, so you have to be pretty quick. And then the other one, let's see. That's the fun. So that was at landing, but here's a longer landing. Let's see.
So takeoff and landing is manual. It's basically just.
For this time it was manual, but now we have it, it's fully automated.
Okay.
It's a fully automated autonomous system now.
Vision based or sort of radio.
It uses Piccolo, and they have their own, the company has their own proprietary algorithm. Is that what you're asking? How there's no vision. No vision.
Okay.
Eventually, though, what they do want to do is have some kind of vision, either LiDAR or something, so that when you're on a ship, if it's pitching and rolling, you want it, so it can track that and then land. But as you can see where we go right now with the Falcor, it's pretty benign. It's pretty calm.
Yeah, it's
Yes.
fast.
This? I'm so bad. Okay, cool. All right. Is that better? No, it's on now, right? So you were asking, there's 4 rotors, vertical rotors, that provide vertical thrust. So 1, 2, 3, 4, and those turn on to take off and land. And there's the pusher motor back here, and when it's in the air, that transitions. It seamlessly transitions to forward thrust. No, the rotors are all fixed. They're all fixed, yeah. So again, for this one, we had a catamaran. So from the aircraft, from the IR camera, one thing we can do is look at in this case, the ocean was cooling during the rain event. So here's an infrared camera before the rain, an image. You can see these darker areas and then warmer areas, but it's kind of simple structure. Here's the rain. You can see the rain falling. It's very cold rain. And then this is what we see. Using this imagery, I can measure both the skin temperature and the bulk temperature. So the surface temperature and then the water just below. And that gradient tells me a lot about the heat budget, what the heat flux is. So here's before the rain here. Then it just starts to rain. You can start to see it. There's a lot more variability in that, and it's actually cooling some. And then when it's really a heavy rain here, it skyrockets. It starts cooling significantly up to minus or 0.6 degrees, which is significant in a very thin layer, which is the order of a millimeter. So the ocean's really cooling fast here. And this is kind of the first corroboration of what people have thought about that the rain cools the ocean very drastically during these intense events. And then after the rain, it kind of relaxes back to its almost initial state. So we're able to do that get away from the ship, not contaminated by the ship, and do that all from the UAV. Yeah.
So 2 quick questions.
Yeah.
So the first one is the measurement temperature
At the surface.
and
No. So we developed a technique separately where you look at the distribution of temperature in this image, and the highest percentile temperature is your bulk temperature, because the physical process is that it's always if it's cold, it's cold, so it's unstable. So it's always in motion. So as soon as it gets to some point, at some point, there's a surface value. Bulk water is at the surface, and then that bulk water cools, and then it sinks. And then so every pixel there is at a different stage of that cycle. And so from the distribution alone, you can get both the bulk and the skin temperature. And we've done that, corroborated that in the lab, and with other instruments that actually come up and penetrate through the skin layer. So yeah, this technique is very, very powerful technique to use. Yeah. Yep. So the flight patterns for this are just simple mowing the lawn. Yep. Eventually, we would like to telemeter back maybe one frame every once in a while to see what's out there, and then target things that we want to look at. But usually in the open ocean, unless there are fronts, it's pretty similar everywhere you look, at least for a given kind of set of conditions. So for a given wind speed, it looks pretty much the same everywhere, unless you're in the coastal area and you have lots of frontal features. So this, I should have put this one first. So this is the infrared image over here, and this is the polarimetric image. So this is actually from the ship, as opposed to what I showed before. But you can see the ring waves that we measure with the polarimeter. You can also see when the rain hits, it creates like a little crater. So we can actually measure the crater that's left behind by when a drop hits the water surface. And then on the right, these are the infrared imagery. You can see just like we saw before, that other image I showed, when the rain hits the water, it mixes it up. You can see all these little patches. See those little patches around there? Little circles that come up? As opposed to this image up here, where those patches aren't there because it's not raining right now. And then this is the same Same payload. We can kind of race through this. So one beauty of doing this from away from the ship on a UAV is that, so typically on a ship you measure the downwelling radiation, either shortwave or long wave, but what climatologists or weather forecasters really care about is the albedo. So from using this, the albedo is just what's coming in versus what's going out. So when you're on an aircraft, on a UAV, you can get away from the ship. You're not obstructed by anything, and you can directly measure what the albedo is. So here you can see, and it's right in line with the canonical values, but there's still a lot of variability. Not the spikes. Those spikes are turns, so forget the spikes. We haven't taken those out. But all this other variability in here is real and significant. So people usually use just a canonical value of 0.5 in a climate model and call it good. But here you can see there's lots of variability just in this short flight. But at climate scales, it doesn't matter that there's all this variability in such a short time. What matters is that it can be significantly different from 0.5, 0.05. And so same payloads I showed before. So this is just shows that most measurements, whenever someone says they go out and measure hyperspectral imaging, they only do it on a sunny day. So the beauty, one thing that we do on our camera, on our system, is we have an upward looking, so we know what's coming in, and we also measure what's coming out of the ocean. So this is a sunny day, lots of energy. This is a cloudy day. So there's still a good, important information here, but nobody likes to go out flying on a cloudy day because there's no satellite data. They only want to calibrate against the satellite data. But from a physics point of view, we really care about both clear days and cloudy days. And this was a cool thing. Remember that catamaran I showed you, or you saw earlier? Whoops. The catamaran, yes, no, anybody? Just say yes. This catamaran. So this catamaran is actually skimming the water surface and measuring what's in the microlayer. So it's skimmed, has a rotating disc. We kind of squeegee off that material, and all the biology and chemistry is measured back on the ship. And one of the things that the biologists found, or cared about, or told me it was important, was this. They discovered these blue copepods in the surface layer. And they were in the surface layer, not down below, because they're food for higher up the food chain. And so they're blue because they hide in the surface, in the microlayer, and they're blue so that the fish can't see them. And here's the black trace is their signature in the hyperspectral, so right around blue perfectly. And then the blue here, the blue trace is the ocean. So you can see that they're just hiding right in the peak of the blue of the ocean, in that ocean. Because not all ocean is blue like this. If you look out here off of the Atlantic, when you get close to shore, it's more green than blue. So we'd be moving out more. So it's important. It's interesting that for this ocean, they migrate to a place where the ocean is really truly blue. And they hide in the very surface layer. Yeah, go ahead.
Is there also sort of a night-day kind of variability?
I'm sorry?
So are those kind of what's changing if, let's say, if they can measure during the night or during the day?
Oh, do they migrate?
Yeah.
Up or down?
That's a good question.
I don't know. I'm not a biologist. That's a good question. I'll ask them. They never measured. They never measured. The catamaran never went out at night. Falcor wouldn't let it happen. Are you guys going to get to do stuff at night on this Falcor? Are you going to fly at night? Question mark. Let me know, because if you do it, I want to make sure we can. Yes?
Is there any link between the catamaran and the albedo? Because the place is the same?
Oh, right. So, you mean for this right here, or anything? Right. So the catamaran's going around, and we would fly over top whenever we could. Is that what you're asking with the UAV? So for the catamaran, that catamaran was only sampling the microlayer. It wasn't measuring any fluxes that we would measure from the UAVs. we would compare the fluxes from the ship with the fluxes we measure on the UAV. So we would compare the fluxes from the shipborne fluxes and the UAV fluxes. So the point of the other, well, this is the other point, is that, so here's this one is that's the Landsat image, right? This is the Landsat image, this is the MODIS. You can see there's much finer detail here in the Landsat, and we even get finer detail with the UAVs. But what we're looking for is this trichodesmium, these blooms of the surfactant material. There's the catamaran skimming all this stuff here. And another thing we noticed when we're flying overhead, so this is infrared image when you have those blooms. In both cases here, there's this cool area here that's right on the edge of that. You can see the surfactant coming into the region. Oh, it's cut off down here, but this cold region here is this region where there's all this slick. So there's changes in the temperature due to the slicks directly, either actually changing the temperature of the surface or potentially changing the emissive properties of the surface. So it could be either one. And to do that, we have to sample this, go back to the lab, do emissivity studies, and determine if it actually changed the emissivity, if it's a different emissivity than the water emissivity. But that being said, here's why we care about this. Here's this trichodesmium bloom in the surface layer, and it's increasing. So you see all this, lots of algal bloom material. This is the temperature, so you can see on the top here, this is positive warming. So the surface is warming because there's cyanobacteria in the actual surface layer, as opposed to, we saw before, the rain was causing it to cool. Here, the bacteria itself are causing it to warm. So we're still in the process of corroborating that. But that would be that's kind of the focus of the next cruise, is going back to looking at the heat budget more than, so in this case it was more looking at gas transfer. The new one is looking, and the new cruise is going to look at the heat budget more. So how these blooms affect not just the heat budget in the microlayer, but the heat budget, in the top 10 to 100 meters.
So how large can be these blooms?
How large? Well, you can see there. Right. Yes, good point. So in this case, this is where? So this is like kilometer resolution. So that's, that's 10, 20, 30, 40, 50, that's 100, roughly 100 kilometers, right? So all this area in here, all this, any kind of light, anything that's not dark blue, any kind of green wisps, those are all little blooms. So all this is all crazy bloom here. But then you have all these other blooms out in the deeper ocean. And so this is, again, so we can look at satellite data and compare against the data we get. So not only the ship data, but we can also compare against satellite data with our measurements. Now I'm just going to show some upcoming collaborations we have. I do a lot of work in the polar regions in Antarctica as well, and I study air-sea processes in polynya. So polynyas, I don't know if you're familiar, polynyas are, so when you have ice up against the coast, you'll have, because of pressure gradient up on the top of the ice cap, it's really cold, dense air. It kind of comes flying down the glacier, and you have these really strong winds called katabatic winds, and those katabatic winds push all the ice off the offshore, and it opens up what are called polynya. And these polynyas are just, when this cold air goes over the water, what did I say before? Ocean never gets colder than -2. You have this cold minus 30, minus 40 air come flying down. There's incredible heat flux here, and it's just generating lots of ice. And when you generate ice, it rejects all the salt in the ocean. So it rejects the salt, it forms ice, and that cold, very salty water forms what is our Antarctic bottom water, which is the beginning of the whole ocean current system, the whole conveyor belt. So we study processes in the polynya, and I've been doing work with the Koreans on their icebreaker, and they have this beautiful helipad, and we're going to start using the UAVs from this helipad. Up until now, I've been putting moorings in, so putting ocean moorings in to study this process. The ship is within 5 years, yeah. So we were some of the first people to use it, yeah. It's a really great ship. But these are the kind of things that we were able to do. So this is using a scanning LiDAR. So you can measure, this is right here. So this is open water in the middle of Terranova Bay. This is where the polynya is, or where we're studying. So the Korean base is right down here, just off the screen. And we can fly our UAV with to measure the waves. So those are the crests and the troughs of the waves, and from that you can get, say, a wave number, a direction, or wave number directional spectrum. Yep. Yep. So flight track is like that. And so it's scanning like across that track. So you can see out here, there's dropouts out here and over here on the wide parts of the scan. And then this, this is out farther over here where there's sea ice, and you can see this is sea ice pattern that we see. Or so you can measure what the open water here, and then you can see what the sea ice distribution, height distribution is. All right. I'll just get to the last project, is this new project up in Alaska where we're working with indigenous communities to understand how sea ice affects their lifestyle. Because they hunt for seals, and the seals live on the sea ice, and the sea ice season is becoming smaller, so they have less time to hunt for the seals, and they're also less time, but also it's more dangerous because the ice is thinner and less stable. It used to be more important. Now it's more of a tradition. It used to be critical because the seals were the food for the dogs, and the dogs were how they got around. So now there's snowmobiles. They don't need dogs anymore to get them around. But back in the day, just 30 years ago, the seal hunt was critical for them to survive. And so we're going up to this Kotzebue Sound in Kotzebue here. You can see there's both land-fast ice and marginal ice zone farther out. This is Russia right here, so we have to make sure we stay away from Russia with our drones, or else they may not come back. But as I said, it's to work. The key part of this whole project is to work directly with the community and understand what their interests are, and then build our science project based on that. And again, we're going to use the same UAVs that we did before, the next generation system with the same payloads, and that's it. I'll leave it at that and take questions, because that's just where we are. Thanks.
So I guess we'll have time for one question up to 15 minutes of questions.
Okay, cool.
The last project, what factor are you looking at?
For this?
What do you think will impact actually the local communities?
So we have worked with, we've gotten to the point where we met with the community for the past year a few times, and we focused in on a bunch of questions that they're interested in. And one question that they're very interested in is this region out here. So as I mentioned, so this area, well actually, yeah. So this whole area in the winter, ice is over. And then out here, there's, it's kind of that ice front out here. They're very interested in what's going on out here at the ice front in the middle of the winter. Like what, so they're interested in two types of seals, bearded seals and ring seals. So they want to know if they're out here in the winter, or do they migrate up the coast or come down the coast. They want to know if there are any predators out there of those seals, so if are there killer whales or something else. We know there's lots of beluga farther north, and we don't know what their migratory patterns are. So one of the things they're interested in is what marine mammals are out at that ice edge. The other one is when there is so the other question is when and why does the ice break up in the spring? That's another key question. That's the crux of the question is when and why does the ice break up? What are the critical factors? So all this land-fast ice. Then the other one is once it does break up and it's in the spring or right before, they have two types of habitats for the seals. So the bearded seals just like sea ice, and they just like laying on the sea ice. So they just want to sunbathe all day. Whereas the ring seals want to be inside in a little den, in a cave. So they want to bury themselves. So they build like little dens for their system. So the local community wants to understand what types, the type of ice why bearded seals are attracted or like to go on certain types of ice. Does it need to be a certain thickness? Does it need to have certain snow cover? Does it need to be slushy at all? And the same thing with the dens. Are the dens well insulated for the ring seals, or are they, what's their structure like of those dens? So those are three. Another one is they've noticed, actually the locals have noticed, there's lots more. It's a lot shallower here, and they're thinking that there's a lot more sediment that doesn't. So these are two big rivers, and they're wondering if they want to know if somehow the timing of the breakup and the melt of the rivers and the sediment outflow is being impacted by when this breaks up. Because if this breaks, potentially if this melts, but the ice doesn't break up, you could have all this sediment coming down, and it's just stuck there at the mouth. And so it just piles up right here as opposed to getting flushed out. So those are kind of 4 questions that they're interested in right now. And then the big question, obviously, is when does it break up and why? So we're going to use the infrared camera to. So we'll be able to identify when they're out on the ice, we'll be able to identify the ring from the bearded seals using both the infrared and the visible. In terms of the den integrity and the sea ice, the IR temperature will tell us a lot about that. And we'll also, like I said, we were developing a sea ice thickness radar and also EM radiometer that'll measure what its thickness is, and so that would tell us something about if they have preferential for a certain thickness ice. And also we'll have the LiDAR to measure, so for the dens, we'll be able to see if they like certain structure, like if they like ridges. So a lot of times you'll have ridging, and they'll form their den right under the ridge or near a ridge. But yeah, those are the kind of things we'll be looking for. Yeah. Yep.
So, if you were to select a few features that are nice to have in terms of UAVs, what would you like to have in the future?
So the key for me, I want to be able to fly from a ship. And to fly from a ship, actually, let's just use that one. That's fine. So it's a huge superstructure, right? The helideck is back here. The wind, so to fly, the wind's coming right at like this. You can think of it. You guys are all engineers. You took fluid dynamics, right? You have boundary layers. Remember boundary layers? So when you have a turbulent boundary layer and it's going up over the ship, there's near the surface is a transition from your laminar sublayer to the turbulent upper outer layer. So when you're coming down through that is the most dangerous part. So if we want to, right, because it's like it's really windy, really windy, and then there's nothing, and then it just kind of drops out of the sky. So that's having the whole LiDAR system or something, some visual system would help, at least a little bit. But I think working on different landing capabilities or somehow addressing that issue would be beneficial. And I don't know exactly how we could do that yet, unless you either just say don't fly in certain wind speeds, or don't land in certain wind speeds, or you model it so you know what you can predict that transition layer, but that's pretty difficult, I would say. Is that the question, or is that what you were asking? Is that the question?
Yeah, so kind of nice to have, let's say, if you were to.
A nice to have would be, well, who was talking about de-icing yesterday? Andreas was, yeah. We were talking about that, definitely for the ones in the Arctic and the Antarctic, to definitely have de-icing systems on there, more proactive de-icing systems. Right now we have temperature sensors that we telemetry data back, and we just use temperature relative humidity ratios or combinations to determine if there is, but then you don't know where or how it's already been impacted or not. So I think Andreas has ideas about being proactive for that, or knows a company that does. But yeah, those kind of things. So de-icing would be one. Having some better sensing of during landing would be another one. Those are two big ones for me.
Then again, going back to visual flying, let's say, I mean, because you probably mentioned, let's say, South Seas or so, and kind of
Yep.
high winds. So is that also kind of nice to have, to be able to fly in kind of high winds and making sure that.
For sure, yes. But I don't think wouldn't use this probably. I think with high winds, you probably want to get something a little more substantial, like a predator class, something like that. Like kind of the same thing, right?
Do you see any scenario where it makes sense to use more than one vehicle at the same time?
Always. I think I like to fly at least two, because whenever you want to understand the process, basically the flux is always, for me, I always want to know what the flux is, and then the imaging tells me what the process is. So if I did one at a time, it wouldn't really tell me much because it's not simultaneous. So I always want to have at least the fluxes and some imaging system on there to complement each other.
Which goes to the question, which is the issue of size. So let's say if you're just talking about imaging systems, some of them can increase, right? The initial size of the goes back to the size of the sensors, right?
It does. Size and weight. So a lot of this VTOL system is great. You can get 10 to 15 pound packages. There are definitely systems. So I think we've done what we can with this size. Definitely, to go smaller, you can do cool. I love doing the profiling with the smaller ones. Atmospheric profiling. One thing that I didn't mention, the payload that we're working on is an aerosol payload to measure size distributions of aerosols, both sea spray and or other aerosols. But a lot of the many things that we want to measure, at the precision we need to measure them, are very difficult to miniaturize. So I think rather than miniaturize them using bigger UAVs, slightly bigger, just a little bit bigger, so we can get up to 20-pound payloads or 25-pound payloads, would be really beneficial. I see that happening before miniaturization of the sensing, because you can always miniaturize something, but it's usually at a cost of your precision and your accuracy, And for a lot of the things that we do, we need really high precision measurements.
Another really good question. What about, let's say, so if you want to measure sequences or so, UAVs, really want to fly as low as possible, but it's got to as close to water as possible.
Yes.
Considerations on that. So how low?
How low? So ideally, ideally, we measure, everything is referenced to 10 meters. Any paper you're on fluxes is always referenced to 10 meters. So the closer you get to 10 meters, the better. Typically, when you're measuring when I was in the middle of the Indian Ocean on a P3, and we went down to 100 feet. And I don't know if anyone's been on a P3 rumbling in the middle, well, just over anything, but in the middle of the ocean at 100 feet is pretty scary because, in a split second, if it just goes like that, it's going in the water. So 100 feet is probably safe, or you can get by with 100 feet, but that's the beauty of a UAV. You don't have to worry about being on there. So I would say at least 100 feet, 30 meters or so, but ideally down to 10. Because we'll just live with that. At 30 meters, you can get you're in the boundary layer to get the flux. Again, boundary layers, guys. So we care about the surface boundary layer, not the free stream boundary layer, because that's where all the flux is before things get vectored away. You guys are engineers, right? Who remembers boundary layers? Anybody? You're a mechanical engineer? You're an oceanographer. You don't count. Come on. Really? So you guys are all computer science engineers? Or double electrical engineers? They stay away from boundary layers? Right. Okay. So that's surprising. So not many aerospace or aeronautical engineers? You are? Okay. So you know boundary layers, right? Okay. Whew. Yes, yeah. That one? So for a full operational shipborne system, it's about 250 US, 250,000 US. For the ones, if you don't need all the shipborne capabilities, and when I say the shipborne capabilities, it flies the same. Everything flies the same. It's just how it communicates. So all the telemetry and there's extra radars and transponders, so that you can fly farther over the horizon and things. For a coastal version, just where we don't need all that stuff, it's maybe 175 US.
Can you say a few words also about this? I think that's the issue of certification, making sure that you would fly from top load.
It is an issue. Where's a good picture?
People don't like to have their UAVs crashing.
No, they don't like anything. I guess that's the only map I have. I know. I got a good map. So here we go. So in the U.S., we have anywhere, on any coastal area, there's what is it? It depends on the country, but usually the coastal area, 12 nautical miles from the coast, is off limits for measuring data. So any country, and then out to 200, is it 200 nautical miles or 150 nautical miles? You need to get permission from that country. So for us here in the U.S., for me to fly up here in Kotzebue, I can't fly anywhere along this coast ever on this project. I can fly within line of sight, no problem. Because the weight limit of the aircraft is above the 55 in the US, 55 pounds, I have to get permission from the FAA. So while I can fly line of sight, but I still have to get permission. So I have to go through the permission or permitting. And then a second permit I have to get to fly through this area, this 12-mile zone. I can fly a direct line through, and that's all I can do until I get out beyond there, and I can do whatever I want out here. But I still have to get permission to do that. If I had, if you want to fly in this area, you basically need a chase plane. So if you're going to do a chase plane, why are you going to use a UAV? Just use the plane. That's why I was saying yesterday, I'm like, if I do coastal work, if I really want to do it, I'm not going to use UAVs. That's why my push is to do it from ships. So from ships, though, you have the issue of dealing with all the countries in the world. And especially depends on where you go. So when I go in for this cruise, we went out, as you can see, we went off Australia here. They're not that difficult to get permission from. But again, they have that same 12-mile area. And you just have to get permission to work in their waters. It's the same kind of permitting you have to do. Any oceanographic vessel has to do the same thing. If they want to take data in the EEZ of that country, you have to get permission from that country. Otherwise, you have to turn off all your instruments. So it's more a matter of you can't take the data. You can fly and do everything, but you just can't take any data. So you have to get permission to take the data in those regions. But also, they probably won't. Once you tell them you're using UAVs, then they want to push you on that, even though they don't have to. So when we were out here, there's lots of little islands that you have to worry about, and they're all their own little jurisdictions. So there were certain areas that we flew out here specifically where we didn't bother. We didn't have to bother with it because we were in international waters. Is it? It takes a long time. I wouldn't say you have to plan ahead for sure. I wouldn't say it's difficult. It's time consuming. So for the one that we're doing in 2 years, I told Victor we got to start now to make sure. Good. Thank you guys.
Thanks very much.
Thank you.